Hi there, this is exercise 6b for some year 12 further maths students. We're doing this in a slightly funny order. Other than that, it should be fairly straightforward, he says, hopefully. Let's get cracking on this and see what it involves. So first of all, I want to show you something about logarithmic functions where they're very similar in some ways to trigonometric functions. I mentioned this on the last slide. So if you have, for instance, tan of some number, I'll say tan of x equal to 2. Then you'll be quite happy to know that x is the inverse tan of 2. I should point out that you could write this as arctan of 2 as well. You possibly have seen that before. Arctan is just another way of writing inverse tan. It doesn't matter which one of those two you write. Probably you're going to use this one, but just be aware arctan can be written. And x then, I'm going to type this into my calculator. It's the inverse tan. Make sure you're in radians. I've just nearly got that wrong. So I'm going to do this in radians. I need to shift set up. My angle unit is radians. So inverse tan of 2 equals, and it's 1.1 and a bit. 1.107. And then alongside this, I want you to be aware that you could theoretically have exactly the same scenario. Tan x equals, now I know tan x doesn't go above 1, I'll show you that in the graph again a bit later, but so I'll pick a different number, 0.8 will do, and therefore in the same way I can write, well, x equals the inverse tan. The reason why we like these is the similarities between them, the inverse tan of 0.8, so it's almost an identical method. And just be aware again, this can be written with some, this was arctan, and for some strange reason, I've never quite sussed why, we tend to write r-tan here. So r-tan of 0.8, and you don't write the c. And again, I've seen other people tell me it mustn't be arc, but I've seen people write it anyway. I don't think it really matters. And if I just do this on my calculator, now on the class whiz, to get the hyperbolic functions, you have to press the option button underneath shift in the top left corner. So I'm going to go option, hyperbolic is number 1, and inverse tan is 6. I'm going to press the inverse tan of 0.8, and it says on my calculator 1 point. So it's quite a similar answer, just by pure fluke, 0.99. So we've got these two answers. I want to show you the reason why I'm particularly interested in the inverse tan and the inverse hyperbolics generally. So just remember that answer. I'm going to erase all things on it, but that was the inverse tan of 0.8. And this is the reason why I wanted to look at it, because there's actually formulas which have logarithms in them. So the inverse sine have this log formula, the inverse cosh has a log formula, and the inverse tan has this formula. Now, of course, we were just doing the inverse tan of 0.8, and we found it was, I've still got on my screen, 1.099. Now why does that matter? Because let's just check it in this formula here. So the inverse tan of 0.8, now obviously the x is 0.8, so I can substitute the 0.8 into here, and it will give me, if you like, an exact answer. The inverse tan of 0.8 then, of 0.8 equals, now it equals a half of the log. Now 1 plus 0.8 is 1.8 divided by 1 minus 0.8 is 0.2. Now if I do 1.8 divided by 0.2, that's 9. So it's a half log 9. Now this is, and interestingly, of course, when you do logarithms, the half can move to the, so that actually becomes then log 9 to the half. And log of 9 to the half is log of 3. Now any one of these three you could type into your calculator. I'm just tempted to see what it is now. I'm going to type in log of 3, and it's 1.09. So this is a way to get an exact answer for these hyperbolic inverse functions. I've just noted there that the fact that r shine can be written instead of shine to -1, but just be aware of that then. So a bit further on in this, these are the graphs that you're meant to learn. It's probably worth you drawing them into your notes. So the graphs of the inverse hyperbolic functions, you may recall that these are meant to be, well, shine x, if you remember, look like that. And so these are always reflections in the line y equals x. You just reflect them in that line, and that always works. This one, which we'll be a bit more careful, this one's actually here. Now, this is not actually a one-to-one mapping. This is many places go to it one mapping. So therefore, I have to restrict it. I get rid of this bit, and it is this part of the curve which I reflect in this line y equals x, and that's why it looks like this. So it is the U shape reflected, as in what you're meant to do with inverse functions, and you'll see that in the next couple of lessons when we do functions in normal maths. So it is this, but it's not the whole of it. So this is the inverse of it. And this one, you may again recall that the inverse tan graph, I think from memory it looked like that. Went up to 1, down to -1. And you can see that repeating itself here. It's just the same graph just being reflected. And the 1 and -1 now are left and right rather than up and down. But these graphs then you're meant to learn. I'll talk to you about the domain and range. Now the domain are the numbers that can go into a graph. We saw this in functions. So the numbers that go in, you'll notice left and right, any number can go into this. Our inverse shine, doesn't matter what you put in, you can type it into your calculator. Whereas the inverse cosh, because of the way this graph starts at 1, it's got to be greater than or equal to 1. The inverse tan, again, it doesn't go beyond there or beyond there, so it has to be between -1 and 1 that you put in. In terms of the range, these are the numbers you can get out of it. The inverse shine, that actually carries, it looks like it might stop at some point. It actually carries on going and going and going. So that's why it says all numbers. F of x belongs to the real numbers. Whereas for inverse cosh, it's got to be greater than 0. Again, notice this, it never goes below that axis. There's nothing below that axis, so therefore it's greater than 0. And the inverse tan, I think that's the most obvious one. You can see that it does go on and on forever. It goes down and down and down forever. The fact it doesn't go that way doesn't matter for the range. All that matters for the range is what happens up and down. F of x belongs to the real numbers. So if that's true, I've got the answer down here already. So let's, this says let f of x equal 1 minus the inverse cosh of x over 3. So what I haven't written down here is I want two things. I want to know the largest possible domain for this graph. And on the last slide I wrote down something about the domain of this graph. So it's an inverse cosh graph. Now x has got to be bigger than 1. That's what that says. So the domain of this is x is bigger than 1. But you'll notice on this graph I'm dividing by 3. So if you like, x over 3, if I'm looking at a domain, has to be bigger than 1 or equal to 1, because that's what it said before. So I think therefore x is greater than or equal to 3 on this. I've just realized these are the wrong answers. These are for the next question, so I can get rid of all this rubbish down here. X is greater than 3 is the domain, and I should really say this is the domain of this graph. And the second thing I want is to, given that x is bigger than 3, I want to know what the range is. So again, it's probably worth me thinking about the actual shape of this graph. I'll just turn this around so it doesn't look so ski-whiff. So this is a normal one. That's the inverse cosh. Now I've got to minus it. So straight away it's going to look upside down. Oh, I've got a +1 on it, so it's going to move it up 1. It's a translation. So if I was to draw my best version of this, it will start up there at 1 and it will go down like that. That's what this f of x curve looks like. And for that reason I know that the range, again the range, always look what happens up and down, and the range I think basically goes well, I said that was at 0 and it moved up 1, so I think the function is such that it's always less than or equal to 1. And that's what I've got as well. Yes, I agree with that. So anyways, let's go on to the next question. It says solve the equation sin x equals 7. Now, we are going to try to do this as accurate as we can. It's like the ones we did before. It's the inverse sin of 7. And therefore x equals, now it says it here, that's a 7 and that's a 7 squared. So it becomes the log of 7 plus the square root of 1 plus 7 squared. So you can see this is the log of 7 plus root 50. And it's not very nice, but that's the answer. And of course root 50 is 25 times 2 rooted, which is why we can say it's 5 root 2, and that's why this answer is slightly better down here. Given that cos squared minus cos x equals 2, find the answers to this. And he wants exact answers. Now, first of all, I'm just looking at this thinking this is a disguised quadratic. So I'm going to tidy it up a bit. I'm going to make it equal to 0. I'm going to chuck that into my calculator with, so mode A. It is a polynomial of degree 2. And I've got 1x squared, I've got negative 1x, and I've got negative 2. And it tells me in my answers, and it says x1 equals 2, and x2 equals minus 1. And that tells me that cos x equals 2, or cos x equals minus 1. And remember, I'm going to have to inverse cos, and I can only inverse cos if x is bigger than 1. So I know this one will give me no solutions, whereas this one will. X is the inverse cos of 2. X is log. Now again, that's a 2, that's a 2. 2 plus log, I reckon log 3. You'll notice I've got up down here a plus or a minus, and that's because when I square root I've got plus or a minus, so I suppose I'm quite happy doing that. Okay. Show that this equals this. So I'm going to run through this. This is a proof, if you like. There's a bit probably more than we need, but I quite like this. Now the trick here is to start off and say, well, let y equals this thing we're going to do. Of course, this is the formula which I gave you just now. So this is a proof of that formula. So I start off by saying y equals this thing, and I turn it round, and by moving the sin inverse onto the other side, I get x is sin y. Now, to do this, I need to know an identity. Now, we already know that cos squared x plus sin squared x equals 1. Well, there's a similar thing here. It's cos squared x minus sin squared x equals 1. It's this. For this reason, you see, I can rewrite, it says here, sin y. And I'm going to need that in the bit. So anyway, if I just play around with this a little bit more, you can see I get cos squared equals 1 plus sin squared. And therefore cos equals the square root of 1 plus sin. And that's what really all I've said here. But the critical thing, of course, is that sin squared is x squared, which is why I've written 1 plus x squared. So we needed to know that. Another little trick here is that, and again, for now you're going to have to take my word for it. We're going to come to this later. We have this second identity for e to the x, which I've written down, and I tidy this up, and essentially that allows me to write this in a neater form. Have a look at that, get your head around it. I can always come back to it a later time, but I suppose the only tricky bit is here. We've had a couple of these we haven't seen before. So have a look over at the exercise.